see, diode D. Okay. Okay. So this is my circuit. So this was what we have analyzed. So first of all, what was the application of the circuit? So why we use this? This circuit is called clamper. This is the circuit which consists of a diode, resistor, and a capacitor. And this is used to shift a input waveform. A shift a waveform to a different DC level. Okay, we are clamping. I already discussed. We're clamping a DC over this input, and we get an output V0, which is clamped input. Okay, so it is shifting the DC level. Okay, without changing the shape of the signal or without changing the appearance of the signal. Okay, okay, and there's one question capacitor charging regarding charging discharging capacitor. We should understand that the resistor and capacitor of the circuit must be designed or chosen in such a way that the time constant, as we already discussed, time constant RC is sufficiently large to ensure that the voltage across the capacitor does not discharge significantly. Okay, during the interval, diode is non-conducting. Okay, because when diode is non-conducting, the capacitor input is connected to the output, right? When a diode is not conducting, you can see the input, and this is the circuit. You can see diode is not conducting. This is the circuit. Okay, so output, what is the voltage across output? The V in as well as VC, voltage across capacitor. At that time, we have to make sure that capacitor doesn't discharge, so that it acts as a perfect DC voltage. So what to do? So the capacitor is not to discharge. That means we have to choose the values of C and R. RC time constant should be very large. Okay, so that capacitor don't discharge during the phase where diode is off. Okay, so that is a non-ideal thing. So but you should understand the capacitor, there is a discharge option, but we are not allowing capacitor to discharge. For example, there's a time constant like 5 time constant, 3 time constant. What time constant? Tau. Time constant RC, right? There's a time constant RC which decides the time required for the capacitor to charge and discharge to a particular level, maybe 63%, 90%, etc. So if we keep it larger, the capacitor will retain the voltage, so that we'll get a perfect output square wave, right? So what is comparison? It should be compared with the input signal. For example, whatever time constant we have to decide for the circuit will depends upon the time constants of the or the time duration of the input square waveform. Okay, so compared to input square waveform, our capacitor should retain the voltage to a greater time. Okay, so ultimately reference is our input. So if we don't need to keep a large time constant, because our input time constant should be, or the capacitor or RC time constant should be greater than the given input time interval, half of the given time interval, but we need a square wave. Okay, so that is only in the half of the t by 2, 0 to t by 2, 0 to t by 2, our capacitor at least should be retain its charge. Okay, so its RC should be greater than that t by 2 time, whatever. Okay, so leave non-idealities. Now let us come back to circuit. Okay, so first, what way of analysis? The first thing to see is, the first step to analyze is start analysis by examining the portion of the input signal which forward bias the diode, right? So here diode should be forward bias. Initially the diode has to be forward bias. So this should be plus and this is minus. That means diode can be on only when the anode is positive and anode is negative. That happens in the positive cycle, right? Positive cycle. So we should start analyzing the circuit with that input cycle which charges the diode. Why? Then only we can get the voltage across the capacitor VC. Okay, if this is plus, then the capacitor one plate will be plus, other plate will be minus. So what we got? We got the capacitor residual charge. And what is the output? Output will be 0 in this cycle, because diode is short circuit, we can say. Okay, so output will be 0 at this time. Okay, and the other cycle, when the input is going to negative cycle, what happens? The negative cycle, the capacitor is going to be, sorry, the diode is going to be off, right? That is going to off. So there is a open circuit diode. Okay, so what happens? You don't need to consider this part of the that part of the circuit, and now this circuit is considering V in, VC, and V output. Okay, so what is V out? We can see In negative phase, V in is like plus and minus. You can see this plus and minus and this plus and minus VC will be add on together and we'll get minus VC plus V in the output, right? Negative level. So you can see what is the output of this circuit which we had drawn just now. Your input will be like this. This is your input. Positive cycle diode is forward biased. So diode is forward biased and the positive cycle output is 0. Okay. And the reverse cycle, what happens? I know the both voltage of capacitor and voltages of the input is coming across. So it will be like this. Again 0. Again negative. Likewise. Okay. So what is happening? Initially my DC potential was 0 volt. This was my DC level. And plus 5 or minus 5, whatever voltage plus V and minus V plus or minus 5 was there. Right now I have given a DC shift to plus minus 5 DC shift to the my input signal. So what happens? Now my 0 and minus 10 is my maximum DC ID level. Getting? So this is clamping in a negative voltage. I'm giving a DC, adding a DC level to the circuit. Okay. Okay. So now I'll draw another circuit. You have to tell me what is the output of that circuit. Okay. So again, I give a square wave and I need a capacitor. Okay. Now I give a diode. Now what I'll give? I'll give some voltage source. Okay. Parallelly I keep a resistance so that I need to get an output here. Okay, so this is V in, V input, capacitor is the diode, and V output across resistance. This is R, and this is VB bias voltage, VB, VB. This is plus, this is minus. Okay. So what is the difference happening in this circuit compared to a previous circuit? Yes. Can you draw the circuit in a notebook? And there is only one thing, we are adding a DC source. So that comes in the two cycles, positive as well as negative. So we have to analyze those two cycles with respect to this voltage. That's it. And you can assume VB is less than V input. Well, I give it condition here. So I'll say the V input is plus 10, minus 10, negative cycle, and VB is you can take it as 4 volt. VB is 4 volt plus 1. Just for some practical, uh, you know, practical considerations so that we can draw the waveform. Okay. So what happens? So we'll start analyzing. When we start analyzing, what is the important point? Again, we have to start analyzing the circuit with that part of the input waveform or input cycle which forward biases the diode D. Okay, so we know which portion of the input forward biases the diode. Definitely it is negative cycle, right? Because cathode is at the top. You can see the cathode is at the top, anode is at the bottom. So which cycle forward bias the diode? When input should be negative, and that happens in negative cycle, right? Okay, so I'll start as analyzing with the negative input cycle. So you can see I'm just using blue color. So this is I'm analyzing the negative cycle. Okay, so when negative cycle comes, I know minus input is minus and plus 10 volt. Can assume this is a DC voltage coming across the capacitor. Okay, minus plus 10 volt, which is forward biasing the diode. Okay, Now we can assume diode is forward biased, is connected, short circuited. Now let's calculate VC right now. What is the VC right now? Other like unlike the other circuit, previous circuit, there is a VB, the bias voltage. Now we can see that uh, the both both the input as well as the VB is going to affect the capacitor, right? You can see the input combination is going to give a negative plate, a minus 10 plate on the left side of the capacitor plate. And same time, we can see the VB. VB is going to give a plus 4 here, plus 4 here. That means the input is going on giving negative charge on the one plate. So what is the net effect? What is the potential difference across the terminals of the capacitor? That is simple. Just see the potential difference across the terminals of the capacitor. What is this? You can see, it is 14, right? It is 14 volt. That means both the input and VB is going to act as a series of battery supply, right? You can see the sign minus plus, again minus plus. Both are going to add. Whichever way you can see both are going to add on to it. Plus minus, if you go from left to right, you can see plus minus, again plus minus. Or if you go in the reverse direction, you can see minus plus, again minus plus. So though VB as well as the input is going to put its potential difference across the capacitor. So the capacitor will be charged how much? Capacitor will be charged. Capacitor will be charged. This is minus 10 in this and plus 4 in this. So net voltage will be 14 volt across the capacitor. The sign given here, plus minus 14 volt. Okay. So how to write the Kirchhoff equation here? Let's take VC. So first we have to do, we have to take VC at VC only. I'll take a VC, and this is minus. So I take this VC. Okay. Now let's calculate. V input is plus and minus. So minus 10. Again VC minus plus VC. And again VB. VB is plus and minus. It is minus 4 equal to 0. Okay. So VC is equal to 14 volt. Okay. You can see from this equation VC equal to 14 plus 14 volt. Okay. Okay. Oh, then what happened? Now we have calculated VC. Now what is the output here? Just remember what is the output here at this point. Your diode is short circuited. So output is getting the VB only. That means plus 4 at this point. Is it clear? Okay. So here in this negative cycle, whatever we discussed, we already saw the voltage stored VC across the capacitor. Okay, it is a combined action of the VB as well as V input. Okay, and what is the happening at this cycle in the output? We have a plus 4 in the output because my battery VB is short circuited to the output, parallel to the output V0, and diode is ideal diode. I'm assuming ideal diode, so no need to think much. So I'll get VB plus for an output. Okay, now analyze the positive cycle. When positive cycle comes, what happens? Diode, the VC already have VC charge across capacitor is already minus plus 14. So here I know 14 volt across the capacitor, and I have what is the input? How much I have? Plus minus 10 in the input also. Plus minus 10 in the input. So we can see both will be adding on to each other. You can see if you see the direction here also you can see plus minus minus plus. Sorry, minus plus minus plus. Okay. So what will be the output? Output will be minus here. sorry, here will be plus, here will be minus. That will be V0. How much? 14, 20, sorry, 24, 24 volt in the, okay. I'm writing everything in the same board, so I think it may be a bit difficult for you to understand. So I'll just do it again. Okay. So right now we are assuming positive cycle. What's happened is positive cycle. Okay. And we have diode already. Sorry, capacitor and diode, and then this direction your diode will be off. Okay. And now we have a resistor. Okay. So there is no need to consider this VB. So VC. Okay, so what is the charge across the capacitor? Minus plus 14, 14 volt. Okay. And input we know it is input is already plus minus 10 volt. So V input and we have V output. So starting, I'll assume convention like this plus minus for V0 because I don't know the sign. So let's take, now we apply the Kirchhoff law. Okay. Kirchhoff law, which circuit? This circuit, the combine this circuit. Okay. Okay, the outer circle. Okay. So I'm writing the Kirchhoff law starting from VI minus to plus, plus 10, then again minus to plus, plus 14, then plus to minus, minus V0, 0. Okay. So what is V0 here? So V0 will get 24, right? So V0 will get is 24 volt. Okay. So we are right now we analyze both cycles. In first negative half cycle we got a plus 4 volt in the output, and positive cycle we got a plus 24 volt in the output. Okay. Let's see the compare the waveforms in two cases. Okay. So this is for my input and this is for my output. Okay. So what is my input? A simple square wave. Okay. With values plus 10, minus 10. Okay. Now what about output? In positive cycle, okay, first I analyze negative cycle, right? Because the diode is forward bias and that cycle. In that cycle, what I got? At that cycle, I got plus 4, right? Okay, that cycle, I got plus 4. Okay, plus 4. And the positive cycle, I got plus 24. So the output is like this. Continues. Somewhat like this. Okay, so this is my output, and let me write the, this is plus 4 volt in the positive cycle and plus 24 the positive cycle, negative cycle plus 4, positive cycle plus 24. You can see the input is not changed actually. Input is, the shape is remaining same. You can see the shape is still remaining the same. And what is changed actually? It is the DC value is changed. You can see the shape is still the same. Staple remaining the same. And you can see the peak to peak. What is the difference? Peak to peak voltage from the input. You can see peak to peak is still 20. 20 to 24, 20 volt difference. You can see the difference is 20 volt. The same as the input. Can input also there is 20 voltage negative to maximum. But in this case, what I have got a shift of, how much shift I got the input? 10 plus 4, 14 volt. I got a shift of 14 volt. Right? Initially it was the ground. You can see the initially the ground was at 0 volt. 0 volt here. Now, where is my ground? Ground is symmetrical circuit is how much? It's 14 volt. Okay, and 10 in the top towards 14 and minus 10 towards the bottom also. Okay, so I given a DC shift of 14 volt because my DC voltage VB was adding on to the capacitor voltage. Is there any doubt what we have done? Shape is remaining same, but a DC shifting. Now, in case if I have connected the diode reverse, if I have connected the not diode, if I connected the battery voltage VB opposite direction, what might have happened? That means in this problem, I have a capacitor and I connect diode was like this. Instead of connecting the VB like last time, if I have put like this, so this is V out, this is capacitor, V in, diode. Now VB is, I am reversing the direction of VB, minus and plus. Okay, it's capacitor and diode. Now we can see here, when diode will be on, diode will be on when anode is positive, this is negative. So that is the input you have to assume that cycle, analyze that cycle, from that cycle start as starting point. How much? 10 volts. So you take 10 volt in the input. So this will be the our input cycle, which this is negative cycle, which forward biases the diode. Okay, this cycle is forward biasing the diode. Okay, so we'll start analyzing with that cycle. Now we can see the battery voltage VB. Say for example, VB is 4 volt, like previous example, 4 volt. Now we can see both the input and VB is not in same direction. You can see input is giving negative voltage to one terminal of the capacitor, and VB is also going to charge a negative potential on the opposite terminal. So both are trying to compete each other to charge the capacitor. Okay, so net voltage across the capacitor will be whichever is greater voltage. Say input is giving minus 10 over the one plate, and VB is giving minus 4 on another opposite plate. So net voltage of the capacitor will be minus here plus here. How much? 6 volt. You getting? Next, net will be 6 volt across the capacitor in this direction. Okay, any comments? Yes, you're getting? Okay, so what happens? Capacitor voltage we got minus plus 6 volt in this direction. Now, what is the output voltage at this time? At this voltage, we can easily see the output voltage is minus 4 volt, minus 4 volt across the output. Okay, and bottom point is we got the VC also minus 6 volt. Okay, now what happens? Yeah, any doubt? I think somebody has on the Vinay. Vinay Kanojia, can you mute your speaker if you don't have any doubt? Okay, so anyone has any doubt? Okay, so what happens in this case? In this case, you can see the when the negative cycle, I have output is minus 4, and capacitor has already charged into 6 volt in this direction given shown here. Okay, now in the positive cycle, what will happen? Now in the positive cycle, is coming, so I have plus here, minus voltage in the input. Okay, as shown here, and the diode is cut off. You don't need to worry about the diode, right? Okay, it's cut off. Now you can see the input, capacitor voltage, and output is coming across single loop. So if you apply Kirchhoff voltage law, what we will get? We can see that both input and capacitor are right now same direction. Input voltage and capacitor voltage are right now also same direction. So what is the net voltage? 10 plus 6, 16, right? Okay, and that will be coming across my output in which direction? Plus minus, right? So my output will be in the positive cycle, my output will be 16 volt. Okay, so how I got this? Because I just used Kirchhoff law. Minus 10, 10 input, minus plus 6 VC, and output minus V0 in the output equal to 0. So I got V0 equal to 6. Sorry, there is a mistake. Minus 10. So minus plus 10. Okay. Plus 10 plus 6 minus V0 equal to 0. So V0 equal to 16 volt. Just applying Kirchhoff law. Okay. Now what will be my output? This is for input. This is my output. Okay. So input is simple waveform. Okay. Output. What I got? The negative cycle. I got minus 4, right? Minus 4 negative cycle. Minus 4 negative cycle. And plus 16 in the positive cycle. Plus 16 in the positive cycle. Something like this. Now how much have my voltage has been raised, clamped? So initially you can see this was plus 10, plus 10, minus 10. Now it is plus 16, minus 4. You can see the difference, the level, the shift, how much is it? Initially it also total from minus to minimum point to maximum point was 20 volt. Here also it is 20 volt. Shift is, so how many shifted? I have shifted it. So I have shifted the symmetrical or the middle point of the uh, middle point of my input value to a higher voltage. How much is input voltage? I'm shifted. Yeah, initially it was zero. Zero voltage was my y-axis symmetrical point of my input. Zero voltage. Now what is my symmetrical point? What is my midpoint? Yes. Yeah, it is 6 volt, right? I think it's 6 volt. Yes, it is now. It is changed to 6 volt. Is my 6 volt is my point. So I shifted up to, I think, 6 volt. Yeah, 6 volt up. I have shifted clamp. I've clamped the input to 6 volt plus 6 volt. Okay. So this is the clamper. So that's it. I think. Any doubts, anyone? Anyone has any doubts regarding the clamper circuits? See some comments. 6 volt is yes. 6 volt shifted. Yes. So Rajnish again asking if we interchange the polarity of capacitor. Again, I have to say the same thing. Here you can see. Did you see any difference in the capacitor? I had drawn the capacitor like this. What is the shift you are saying? Both are symmetrical. Then why you are asking the same question? Even if the capacitor polarity, look, this capacitor is symmetrical. Even if you reverse the plus and minus and plus, it's same. Yesterday I answered you telling that in the market you may guess capacitor with plus and minus sign. That is cylindrical capacitor, and they had nothing to do with ideal capacitor. Here we are not assuming it is different poles or different capacitor. Yeah, usually there is a capacitor drawn like this. A series plate like this. Yes, one is plus and one is minus. Okay, but here we can assume this is symmetrical. Doesn't matter. All capacitors are symmetrical only. But because of the practical scenarios in the practical cases, where capacitor is used for grounding, especially in the rectifier circuits, they may provide a terminal. That is because of the non-idealities, which is not going to affect in this, at least in the clamper circuits. Okay, so now we'll go to the diode equation. I think we are not discussed, so we'll just touch through the diode equations. Okay, so Bhuvan is saying, please explain the negative cycle. Okay, so the negative cycle was, we have this input and we have a capacitor, and my diode was connected. Yeah, diode was connected like this, and my battery voltage was like this. Okay, okay, and V0, output is V0. Okay, now minus plus, this is 4. You can assume this is 4 volt, and this is plus or minus 10 volt. Okay, sine wave. This is a square wave. So 10 wave. Okay. So starting, we know that has to be forward biased. We analyze starting. So starting should be we have to analyze with the input having negative cycle. Okay, that is minus 10. We can assume that input is having a given input is a minus 10 minus to 10 volt DC voltage, right? That makes the diode forward biased. Okay, so now diode is forward biased, and that is can be assumed short circuited parallel to the output. So what is the output voltage here? You can see output voltage is minus 4 to minus 4 volt the output. Now at the same time, what is going to be charge stored in the capacitor? Okay, what is charge going to capacitor? My input is charging the one capacitor terminal to minus 10 volt in one terminal, and my DC voltage is going to charge the capacitor other terminal by 4 volt. So net effect, how what is the charge difference? Sorry, what is the voltage difference across the capacitor? It is 6 volt difference. So what will be the voltage across the capacitor net? It will be minus plus 6 volt. Why minus in the left? Because my input is having more input voltage than the VB, right? So we got VC in the negative cycle, and the output also we got V0 equal to minus 4 volt. Okay, now having the VC, now we analyze what is going to happen in the positive cycle. The positive cycle, we can see the input is now plus 10, minus 10. Okay, and diode is not on, diode is off in this. Okay, we no need to consider diode as well as the VB also. Both are off. So this is not considered. Now we can consider only this loop. V input capacitor output loop. Okay. Okay. Now just write the Kirchhoff law, and minus to plus 10, minus to plus 6 VC, again plus 6. Input VO, I assume plus minus initially. So minus V0 equal to 0. Okay. So let's see what is V0. V0 will be 16. V0 equal to 16 volt. Okay. So in the positive cycle, I got V0 equal to 16 volt. That's it. This is a negative cycle, and we draw a graph out of this. And with the positive cycle, I got 16 volt. Negative cycle, I got minus 4 volt. So the total peak to peak difference is still 20 volt. Input is minus 10 plus 10. Now output is plus 16 minus 4. So my DC have shifted by plus 6 to the top. Initially it was negative peak was minus 10. Now negative peak is minus 4. So I added plus 6 to my input. So it is like clamped to a positive 6 volt. Is it okay? Graph of VC. Yeah, Rajneesh is asking, please draw the graph of VC. Yes, that is a good question. Let's see. Let's try to draw the graph of VC. Okay. So we know the both cycle. This is which cycle we are analyzing? This is the negative cycle. No, positive cycle. This is positive cycle. Positive cycle, I have plus 6. Okay. Positive cycle, I have plus 6. Right. What about the negative cycle? Negative cycle, I also have plus 6. So what is the product of VC? Let's see. Okay. So I'm going to plot VC with respect to input. So this is 1 minute. So I'll make it small. Okay, this is my input. This is my VC. Maybe I can plot the output also. Okay. Yeah, this is advantage of simulator. If you have simulator, you can just click any point and simulator is going to show the. So this is my input. Okay. So you know this is input VI. Now I'm going to draw VC. VC is always remaining how much? minus and plus. So I just drop VC, so I'm just remaining minus 6 volt. That's like minus 6 volt. No change. Output we already discussed. This this is the output. Yeah, the point is, yeah, your question is why you are asking the VC. You want to see the capacitor charging and discharging, right? So, but unfortunately, you cannot see the capacitor charging and discharging. Why? Because as a designer of a clamper, I have made sure that capacitor won't discharge. How I can make sure that thing? I'll explain you how I'm not allowing capacitor discharge. Okay. So usually, in any RC circuit or something, I have a capacitor. Okay, and I charge the capacitor using some voltage like this, V, plus minus V. Okay, so when I on the switch, this is plus minus. When I on the switch, what happens? The capacitor gets charged immediately because there's no resistance in the circuit. So immediately my capacitor is charging because it's parallel to V. Okay, so it is charging some voltage V. Okay, now what happens? Now I take off. Now I'll keep one more switch here. One more switch here. Okay, I'll keep one more switch here so that you can understand the concept. Okay, now first I on the switch S1 so that capacitor is charged to V. Then I put the switch off. Okay, now I put the switch S1 off. Now I put on the switch S2. Now I on the switch S2. Now we can see a graph, the capacitor discharging. Okay, initially capacitor was charged, so I'll draw the graph of the capacitor here. Okay, initially capacitor has a voltage V, so I'll show it here V. V was the initial voltage across the capacitor. Okay, now when I on the switch S2, what is happening? From V, at the point V, capacitor is, can see capacitor discharging something like this. I'm just taking a simple, giving a simple idea. So now this is for one resistance. This is R. Now resistance is R, and that has a value. So I'll tell this is resistance R1. Now I'll tell I'm going to increase my resistance. So what happens? I'm going to increase resistance. It takes more time to discharge. Okay. Now this is going. I got resistance R2. Now if I again increase the resistance, if I'm going to again increase the resistance, this is R3. Again, I'm going to increase the resistance. Sorry, R4 something. Okay. So what does it mean agenda? According to the value of my resistance file, I take very small resistance. What happened? It may easily discharge very easily R0 or whatever. Okay. So what is the idea? It is the designer choosing who chooses the value of R and C, and that decides the waveform. If I keep a very large R, what happens? It takes long time to discharge. So practically, I get a very big curve. But still, it is impossible to keep on charge for infinite long time. But I can reduce the discharge of a capacitor. So that is how in clamper I tell our as a designer I keep the discharge time tau equal to RC. You can see here also delay tau equal to RC. That is depending upon this resistance and the capacitance tau equal to RC. I'll take tau very tau should be my tau should be taken much greater than my T by 2, or time period is the time period of the input signal should be half of time period much greater. Tau should be much greater than my T by 2. What is T? T is my cycle time of the input. This is T. Okay. This is my T, cycle time of my input signal. So tau should be much, discharge time of capacitor should be much greater than the time of uh, time of my input, half period of my input signal. So another question is time to instant that charging and discharging is very fast. Its time is so instant that charging and discharging is very fast. No, discharging is not fast. Charging is fast. Okay. Why you can see, can I the question is why charging is very fast, because in charging circuit there is no volt resistance. You can go through the clamper circuit and the resistance is charged in the capacitor. When the capacitor is charged, there is no resistance in its path. So charging is instant and discharging is not instant. Discharging is very slow. That is up to designer. Okay. So one minute, I will just get a call. Got a call. Hello. Hello, sir. Okay. So so is it clear that tomorrow we will have the test, right? Tomorrow we should have the test. Everyone is ready? Or is there any problem with anyone? You already done last time. Yeah, you already done last time the circuit, so you can just need to practice something like that, and you can expect maybe one clamper, some clamper questions also, so that we'll complete the applications part. Okay, so I'll just need to add the one more thing, the diode equation. Okay, so we already discussed the diode waveform. So basically we have discussed. Okay, so we already discussed the diode in the ideal. First time we had discussed diode in ideal state. What's ideal diode? We have a diode in forward biased. If it is forward biased, it is the two conditions: forward bias and reverse bias. So in forward biased, I say it is on. It is switch is on, short circuited. In reverse bias, there is no connection. This is forward biased, reverse bias. Okay, this is ideal situation. Okay, forward bias means my anode will be plus, cathode will be minus. This is ideal situation. So I call this ideal. Okay. Now coming to bit practical or real scenario. What is the thing? Now I need more practical aspect of that because I am doing to design practical things. So I'll say in forward there is small voltage drop across the diode. That means a switch in forward is switch is on and there is a small voltage drop. Okay. What is the value of this voltage drop? This is 0.7. A small 0.7 is voltage dropping across the diode. Why is this happening? We already discussed, because of barrier potential. We discussed, right? When we give a PN junction diode a positive in the anode and negative in the cathode, okay, there's a junction formed and depletion region formed, and there is a inbuilt potential. So this potential 0.7 is used to overcome the inbuilt potential. Okay, and this is and switch is done. This switch is on in forward biased, and this on in forward biased. So I call this as forward biased, and we have same switch with a battery 0.7 volt, and this switch is off. The switch is off in the reverse bias. Okay, so there is no 0.7 voltage across the diode also, because there is no current flow only, so you don't need to worry about anything. Okay, okay. So if you plot the first part, the ideal part in a graph, how you'll get the graph? You can see the graph will be, can be like this is graph I versus V. I versus V is the controlling voltage controlling parameter. I is the dependent parameter dependent on the voltage. So how will you the graph will get? You get the graph when current is increasing, there is no voltage drop across the diode. When voltage is decreasing, current is zero. So this is the ideal characteristics of a diode. In second, what we'll get in second scenario, we again draw I versus V. I in y-axis, V in x-axis. Now we'll say there is some voltage drop across the diode in the forward and reverse direction, it is zero. Okay, this voltage is 0.7. This voltage drop is represented by this Okay. Now, what about this third approximation? We have first approximation, second approximation. Now let's go for third approximation. Third approximation also we have a diode, and in this diode there is a switch and it is on when forward biased, off when reverse biased, and definitely there is a battery and there is a resistance also. Okay, so this voltage of this battery is same as previously 0.7. This R is varying resistance, and this is a switch on and forward biased. This is on when forward biased. Okay, and similarly the same is the case when the reverse biased. When it's reverse biased, the switch is off, other things remain the same. Okay, this is reverse bias. So how will the graph look like? Yes, the graph look like this. It's a graph I versus V. Okay, and you can see this look like something like this. This you can is slanting. There is some slope here because of the resistance. Okay, so this graph is, yeah, definitely this is non-linear because this is not a straight line. There are two things. One is this line, another is this line. So this is not a straight line. First of all, this is non-linear. But resistance is linear. You can see whenever we plot the graph of resistance, we will know that it is linear, right? This is I, this is V. How will it be how will you plot the resistance? It will be like this, something like this. As V increases, I also increase. As V decreases, I also decrease linearly. So resistance is a linear device. Diode is a non-linear device. Okay. Now, what is the real graph? Now we go for the real graph. Now, practically or non-ideally, we have a